Boing, 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 boing. Fun in the sun. Come on. No! It's not what I wanted. Documenting it. Come on. Come on. Come on. Come on, boy. There we go. There we go. Okay, now it's responding. All right, very quickly here. The antiderivative of sine of x with respect to x. Negative cosine of x. Plus c. Thank you. Woo! Thank you. Thank you. All right, we were only halfway there. The antiderivative of cosine. Sine of x plus c. Good, good, good. Secant squared. Tangent of x plus c. Good. Cosecant squared. Negative cotangent. Just x plus c. Good. Secant tangent, Schroeder. Oh, sorry, he's got his mouth full. Okay. There we go. Secant x plus c. And then cosecant cotangent. I thought you'd be ready for that one, but okay. Negative cosecant of x plus c. So those we have memorized. Those are either derivatives, known derivatives of trig functions, or known derivatives with slight corrections, right, of a negative. But really, sine and cosine are the only ones that are just plain old trig functions. So there's 4 others out there that we need to develop. So let's do that for a tangent of x. And we saw this one maybe last week on one of the warm-up or one of the note problems where I was kind of taking an unconventional path. Tangent of x is one you're going to memorize along with the other 3 here. If you need to reinvent the wheel every time you need to drive your car, that is not the most efficient way to get from point A to point B. So, but you could, right? I don't know if it's called reinventing it though, right? Because if it's already invented, you already kind of know about it. Hindsight's 20/20. I don't know. Maybe discover is a better word. If you call tangent sine over cosine, you have a quotient. It might be easier to view that as a product. 1 over cosine times sine of x. And now we have a product of 2 variable functions. Maybe the derivative of one of them, the inside function that is of one of them, is the other factor. So what would you call the inside function? Well, in this case, cosine of x is your inside function. And what is it inside of? Well, it's inside of 1 over blob to the first, right? Well, let's see if it works. The derivative of cosine is negative sine. So we do generate the other factor. We're only off by negative, so we have a negative correction, and the sine of x gets packaged back up. So what is the antiderivative of 1 over blob to the first, or 1 over u? Natural log, absolute value of the blob. Yeah. And so that could also be one of the hard ones to see. Just like anything in the numerator to the first, it's kind of hard to see that it's inside something to the first. When it's in the denominator to the first power, that is the natural log each and every time. If it's any other power or if it's under a radical, it's going to be a power rule. So there you go. Negative natural log of absolute value of cosine of x is the antiderivative of tangent. And you want to memorize that one. But you have the option of memorizing another one and adapting it. That -1 factor in front, remember with logs, we can play with logs. We could bring that one up, and you can actually bring it inside the absolute values and make it an exponent on your argument. Now, is that inverse cosine or the reciprocal of cosine? That's the reciprocal of cosine. That's why it's important to write it like that. The reciprocal of cosine is also known as secant. Yeah. So it's also equivalent to the natural log of the absolute value secant of x. Either one of them work. Either one of them work. The negative natural log of the absolute value of cosine might be a little more useful, like in terms of identifying a multiple choice answer. Okay, so that's tangent. Cotangent then, we can kind of discover what it's equal to by a very, very similar method, because cotangent is equal to the ratio of cosine over sine. So if I write it as cosine of x times 1 over sine, saving a step, the inside function is now what? Sine, and it's in the denominator to the first power. What's the derivative of sine? Cosine. We're not off by anything this time, so the cosine gets packaged up. So we're ready for the second step already. The rider's 1. There's no correction. 1 over blob to the first becomes the natural log of the absolute value of the blob plus c. So there it is. The antiderivative of cotangent is the natural log of the absolute value of sine. Now, there is another one that it's equivalent to, right? Because you can write that as the reciprocal of sine to the negative first power. What's the reciprocal of sine? Cosecant. You can write that to the negative first power. That's the same as sine, isn't it? And now you can bring the negative 1 out front and say it's negative natural log of the absolute value of cosecant. So it's kind of the same idea, but working from the other direction. The ones in terms of sine and cosine show up more often. So just be aware that you can do that, because I've seen a question on an AP exam on a release multiple choice where that alone was the question. Like they give you this and they say which of the following is equal to that, and you just match it up using the properties of logs. So it's all about just increasing your awareness of things that could be done. All right. Now we get secant of x. The antiderivative secant of x. Is it secant tangent? No, that's the derivative, which is why the integral of secant tangent of x is what, Schroeder? You done with your meal? Plus c. Very good. So what is the antiderivative secant? That is, what do we take the derivative of to get secant? Well, you know what worked over here? Writing them in terms of sine and cosine. Yeah? Let's try it over here. Secant is the same as 1 over cosine. All right. So I'm guessing, since it's 1 over blob to the first, it's the natural log of the absolute value of blob, right? That's how math works. That'd be nice, right? No, it wouldn't, actually. It would take a lot of fun out of it, and that's not too nice. You can't just always say that if it's 1 over a variable function to the first, that the antiderivative is natural log of the absolute value of that function, right? That would make a great answer choice A on a multiple choice, right? And the proletariat choose that. Y'all are not the mathematical proletariat, right? Y'all are the elite, the proud, the few. Bourgeoisie, okay. It doesn't work. So that doesn't quite help us. So what else can we do? Well, it's an expression that we have to manipulate. Trig identity? Well, we already tried that. Split up the terms? Oh, there's only one term. What? Half angle? Yeah, some other kind of identity might work, but it's already a single x, which makes it kind of nice already. If I start using any type of angle identity that's going to manipulate it, it's going to either make it x halves or 2x, which is not necessarily what we want. So what can we do to an expression without changing its value? We can add a clever form of 0, plus 7 minus 7. Does that help? No, it doesn't. Or we can multiply by a clever form of 1. Yeah. Now, 7 over 7 is a form of 1. Is that a real clever form of 1? No. But what about like the natural log of e over 5 to the 0 power? That's clever. Clever. Does it help? No. So you have to have the insight knowing what to multiply by so that it fits a pattern that you recognize. And for secant, what was the derivative of secant again, Schroeder? Secant tangent. So maybe, just maybe, if I multiply by secant tangent over secant tangent, but instead of multiplying them, maybe I add them together? I don't know. I'm just taking a shot in the dark here based on what Schroeder said. Right? Helping you out again. Pretty good insight there. Does that help me? I don't know. Let's put that over 1. Is that legal? Yeah. Hey, now I can distribute. Let's distribute. Secant times secant, secant squared. plus secant times tangent is secant x tangent x. All over 1 times that is just that. Okay. Now I have a quotient, which I know I can write as 1 over the denominator, like I did with the sine over cosine, times the numerator, which I'm just going to flip it around and call it secant x tangent of x plus secant squared. I'm going to commute those terms. So this was just a crazy, wild stab. Does it work? What's our inside function now? I have 1 over blob to the first again, don't I? Well, let's see. What's the derivative of our blob? Well, our blob is secant x plus tangent x, so it's 2 terms. What's the derivative of secant x? Secant tangent. Plus the derivative of tangent? Secant squared. Holy moly, smokers. It worked. Good job. It worked. And therefore, we're off by what now? Nothing. Nothing. Not a thing. So the whole secant tangent plus secant squared gets packaged back up. And now we're ready for step 2, the rule of integration. It's 1 over blob to the first. What's that? Natural log, absolute value of the blob, secant x plus tangent of x. And of course, finishing off with plus c on the side. There you go. You're going to want to memorize that one. That one's a little bit harder to rediscover if you forget it, because you have to have that insight. What that Schroeder has. No, he does have. He fueled himself with that meal. Powered the brain. You burn a lot of calories with your brain. It's always important to refuel them. Refuel it, sorry. Memorize that. Okay, now, here's kind of an idea that might help you memorize it if you have a hard time memorizing things. The derivative of secant, of course, is secant tangent. So I say this every year, and it seems to help. The derivative of secant is secant tangent. The antiderivative of secant is also secant tangent, just like the derivative, except for the fact that they are being added rather than multiplied, right? Inside an absolute values, behind a natural log, with a plus c. Yeah. Other than that, it's exactly the same. Exactly the same. All right, sweet. All right, so having said that, maybe you can anticipate what the antiderivative is of cosecant of x without having to derive it in a very similar fashion. What's the derivative of cosecant? Negative cosecant cotangent. Well, it turns out that the antiderivative is exactly the same as the derivative, negative cosecant cotangent. The only thing is it's negative, leave a space, cosecant cotangent, and you're adding them together inside an absolute value inside of a natural log with a plus c. Exact same thing. And you could derive that, you could prove that if you multiply by cosecant plus cotangent over cosecant plus cotangent, it works out very similarly. Okay? So, believe it or not, it does help. The derivative of cosecant is negative cosecant cotangent, so is the antiderivative, but for those 15 modifications or whatever they are that you have to make. Okay? Fits the same pattern, pretty much, more or less, kind of. All right? So memorize those, memorize those, memorize those. Okay, cool. So now we can handle integrals that look like this. We now have a whole another arsenal, 4 new functions that can act as the outside function and therefore the rule of integration for these use of pattern recognition problems like this one. We have 5x squared times tangent of x cubed plus 1. Well, x cubed plus 1 is inside the tangent. What's its derivative? 3x squared. Oh, shucks, we needed a 5x squared. Diggity darn it. Are we okay, though? Yep, because 5 goes along for the ride. We get the critical x squared part. We're only off by a, we have a 1/3 correction. Good. We're off by 3, so we have a correction of its reciprocal. And now the 5 isn't taken into account. The x squared is packaged back up. Step 2, what's the rule of integration? Well, it's inside tangent. What's the antiderivative of tangent of blob? Negative natural log absolute value cosine of the blob. And if you write it like that, shame on you. Because that's not just a grr, that's a what the heck are you doing? Right. Yeah, I'm missing some very important parentheses. So make sure that it doesn't turn into a subtraction problem. And of course that does come out to be negative 5/3 natural log absolute value of cosine of the blob. What if that's not an answer choice? What else could it be? It could be secant? Sure. Positive or negative 5/3? It would change the sign. Yeah, it would change the sign. So either one of those could be an answer choice on a multiple choice portion. So just be aware of that. You can't quite do the same thing that with these two here. Because they're two terms, when you bring the negative one up, you can't just flip both terms. It would have to be the whole quantity in the denominator, so it doesn't work as nicely. All right, you do this one on your mark, get set, go. Yeah, you get it? Same answer? Yours is positive. Dang it, where did I go wrong? Is yours negative? Yours is, you just wrote it because I wrote it. Why did I write it? Is yours negative? Yours is negative because I wrote it or because you wrote it? Because you wrote it. Did you write it or did I write it? You got a positive as well. Man, you could see how there's some tempting answer choices on a multiple choice question. Yeah, it should be negative. That's a good one. I love your sense of humor. Okay. Yeah, I did it using U substitution just because it's a viable method and it's something that we'll have to use later on. I let U equal the inside function. So taking the derivative of both sides in differential form, I get du on the left. Now, don't forget the chain rule. What you're calling the inside function, that inside box, can have nested boxes inside of it, and not just one necessarily. It could have several. You could have 5 variable factors. 4 of those, then, would be chain rule products from that inside box. There can only be one big box on the outside. So the derivative of e to the negative x is e to the negative x times the derivative of negative x, which is negative 1, times dx. So with u substitution, we get secant of u. That's why it works. But then notice I can replace e to the negative x dx if I solve for it by multiplying both sides by negative 1. I can replace e to the negative x dx with a straight negative du. So that negative 1 I can bring out front with the 2, and the du is always the right bookend. So that's the whole idea again behind u substitution. It gets rid of that other factor, which we say just gets packaged back up. It gets rid of it and puts it in a very, very recognizable format. So now negative 2 goes along for the ride. The antiderivative secant u du is the natural log of the absolute value secant u plus tangent u plus c. Just don't stop there. Okay? Make sure then you replace u with what u is, and u is e to the negative x. Okay? Of course, you don't need to do it that way. You can do it by pattern recognition. Just realize that you are off also by a negative. Yes? We kind of run out of variables to use. X and Y are used quite a bit. A and B are used quite a bit. X, Y, and Z are used for three-dimensional things. You don't want to, M and N are used sometimes. A and B, I already said that. L and M, I don't know. You don't want to use X and Y. Those are already used. I don't know. Some letters are just more opportunistic than others. Are you happy with that answer? What else could it be? A symbol? It could be a symbol, right. It could be a symbol. Yeah, now you're getting really unconventional. I like it. The reason that we use U is because U substitution is a method that doesn't work without U. That's why we use it. Okay? And that was long before texting. When people would say, hey, what are you doing? Right? Has Twitter gotten rid of the 140 character limit yet? No? Okay. Because then people are going to start typing out you, right? I mean, it's going to bring back you. When Twitter gets rid of the 140 character limit, you is going to come back. What is what? You? So, okay. Evaluate the following. Let's try some random integrals now to integrate all of our integration methods. I see what I did there. Okay. Example 12. Evaluate the following. Look, wait, first of all, notice A and, well, they all look different. Okay. So, I'm thinking of a different example. We got x over x squared minus 4. Just kind of a random integral, right? We're trying to find the antiderivative. There is no quotient rule for integration, right? So we have a quotient. Now, there are two ways to think about this problem if you don't see it immediately, and some of y'all might. You can either A, bring the factor from the denominator to the numerator, which would be a viable thing to do if it turns out to be a power rule, because then you're set up to just add 1 and divide by the new exponent. Or it could be viable just to separate the factors like we did previously so that you could still see it as a product. Either way, it's going to be the same rule of integration. What would you call the inside function? X squared minus 4. Yeah. So if anything, bringing it to the top forces you to put parentheses around it and put an exponent there so that you can actually see that it's inside something. Because if you walk up to it as is, again, it's not very obvious unless you have some experience to see that it's inside something to the first in the denominator, which I've added when I split it up there. So it is the inside function. What is the derivative of x squared minus 4? 2x. Compared to the other factor, you're only off by a what? 2. So whichever form you leave it in, the original form, you're comparing it to the numerator, or when it's off to the side, you're only off by 2 in any of the 3 cases. So you're going to have a correction of 1/2. Okay, and then the x gets packaged back up. And now the rule of integration is what? Natural log. If you wrote it like that and you tried the power rule, you add 1 and you get 0, and then you divide by 0 or multiply by the reciprocal of 0, that should be kind of a, oops, oh, nope, natural log to the rescue. Absolute value of x squared minus 4 plus c. Don't forget plus c. Okay? Either way. All right, letter B. Once again, you got a constant multiple. If you want, you have 2 factors in the denominator. You can write that as x to the negative first, natural log of x to the negative first, dx. You can write that as 5. You could split it up, 1 over x times 1 over the natural log of x dx. I mean, there's lots of ways to split it up. The key is that you have to recognize the pattern, and that comes from experience. What would you call the inside function? Natural log of x. And again, if nothing else, forcing yourself to bring them to the top puts parentheses around them with -1 exponent so you can actually see that it's inside of something else. Yeah, and natural log of x is a little more complicated than x because x can be the inside function because the derivative of x is not natural log of x to the negative first. It has to generate the other factor. But the derivative of natural log of x is x to the negative first, also known as 1 over x. Okay? So maybe you leave it like this line here because now you can kind of write it like that. And now you're not off by anything because the derivative ln of x is 1 over x. No correction necessary. 5 goes along for the ride. And now what's the rule of integration? What is our ln inside of? It's inside ln, yeah. So ln is not only the inside function, it's the rule of integration. So it becomes the natural log of the absolute value of the ln of x. Now notice the absolute values. The ones that we added for the rules of integration, the absolute values need to be there. But for the ln of x that was already part of the original problem, we don't need to add them there because we're assuming the domain that we started with. Okay? So your choice of inside function and outside function in terms of checking and anti-differentiating, totally independent of each other. They could be the same function. Like you saw in the quiz, the inside function was cosine, the outside function was cosine. Here the inside function is ln, the outside function is ln. All right, this one here, rewriting it. You might be picking up on this. You get 1/4, and that leaves a 1 over x factor times, and then all that in the numerator, that's natural log squared of x. That's how we read that. It's like cosine squared. If you write that whole thing in expanded form, it's the natural log of x to what power? 2/3. Good. What's your inside function? Natural log. What's its derivative? 1 over x. Are you off by anything? Nope. 1/4 goes along for the ride. 1 over x gets packaged up. Part 2, the rule of integration. What is ln inside of now? Power rule. Blob to the 2/3 becomes blob to the, 3/5 blob to the 5/3. I like to leave a space and come back just for instructional purposes. But yeah, if you know it's going to be the reciprocal there, go ahead and put it right away. Just don't forget your plus c. And if you put the 3/5 right away, don't forget your 5/3. That's happened before. Okay, and then you just combine everything in the front. You get 3/20. I guess you could say it's the cube root now of the natural log to the 5th power of x plus c. You could rewrite it like that. Questions so far? So good? All right, you try. That's not just an x in the bottom, that's an e times x. Bless you. Not very slippery. Right. Oh, if it falls in that cartoonish kind of way. Yeah. Right, and then whoops. Yeah. Okay.
Plus, you were using your hand and your thumb on your feet.
Right, and I knew it was there. Yeah. Good. Yeah, this one, if you rewrite it, 1 over e, you can bring it out front, then you're left with 1 over x. Hopefully you're realizing on a lot of these, ln is the inside function. Its derivative is 1 over x. There's no correction. So 1 over e goes along for the ride. And now, since we've got this memorized, the outside function, the rule of integration is cosecant, which, of course, is negative natural log, absolute value of cosecant blob plus cotangent blob. Remember that the blob is still there now in both angles. It's real tempting just to put cosecant x, cotangent x, but it has to be the same blob in both. And again, if you don't put parentheses there, at least pull the negative out front of the 1 over e, and then plus c. Okay. Ooh, this one looks good. Try it. Don't forget your dx. If you ever get stuck, just keep telling yourself, I'm looking for a function that when I take the derivative will give me the original integrand. And so guess, check, revise can always be a good method. I may not give you the answer right away, but every time that you analyze your check, you know, you can revise appropriately. It can be revealing. It can give you a clue to why it's not working. Two variable factors, it's a quotient. If you write it side by side, what it does is it forces you to put grouping symbols around your denominator. So what are really, on this first line that I wrote here, you really only have two choices for an inside function. Either 1 plus x squared is inside something to the negative first. Well, is that going to work? What's the derivative of 1 plus x squared? Arctangent of x? No, yeah, it's 2x. That's not even close, so that's not going to work. What is arctangent of x inside of? Something to the first, right. Now, we don't know how to find the antiderivative of arctangent of x, so that should also, right now, be kind of a red flag. We only know how to take the derivative of arctangent of x. And what is the derivative of arctangent of x? 1 over 1 plus x squared, which might not be as recognizable in the 1 plus x squared to the negative 1 format as it would be in this format, okay? So there you go. The derivative of arctangent is the other factor. No correction necessary. So the entire 1 over 1 plus x squared gets packaged back up. And now we're ready for the rule of integration, which is blob to the first, which becomes 1/2 blob squared plus c. You get arctangent of x. And there's your answer. Now, we will learn how to find the antiderivative of arctangent later on when we learn integration by parts. All right, so if you want to take the derivative of that, you'll see that it does become part D. All right, let's do 13. Well, we have like 2 minutes yet. We'll do it at least one way, 13. Notice it's a definite integral, and that's a little different. Remember, using the fundamental theorem of calculus requires you to be able to first find the antiderivative. So, I don't want to have to expand it out. X squared plus 1 is my inside function. Its derivative is 2x. We're only off by what? 2. So I've got it. If we're only off by a constant, you got it. 1/2 correction, the x gets packaged up. The rule of integration for blob cubed then is 1/4 blob to the 4th. So I was able to find the antiderivative. Do I need the plus c? No. It's a definite integral. So now we'll just evaluate it from 0 to 1. Now, notice I have a 1/2 and a 1/4. That's a 1/8. When you're evaluating a definite integral, I would recommend putting your beefy pink brackets and just keeping that constant multiple out front so that you don't have to distribute and carry it through each time. If I plug in the top now, I get 1 plus 1, which is 2 to the 4th, minus, here's another thing. Just because you have a 0 on the lower interval of integration doesn't mean that your answer is going to be 0. In this case, when you plug it in for x, you get 0 plus 1, which is 1 to the 4th. And there you go. Your final answer is 2 to the 4th, which is 16, minus 1 to the 4th is 1 over 8, so you get 15/8. Now tomorrow we'll pick up there with the same example, but I'll show you how to do it with U substitution. Okay? All right. Have a great day. If we press tomorrow, we might finish. Maybe not, though. Maybe 2 more days on this, so it's looking like a Monday worksheet due date. Have a great day.